Hello everyone, hope you are doing well. So, up to now what we have done is definition of topological spaces in short, a few examples, the distinction between metric spaces and topological spaces, few examples of closed sets and open sets. Now, let me begin with another very important aspect of mathematics. As you might have seen in group theory or vector spaces and the similar structures, given a set, when we associate some structures like groups, so in that we have subgroups, right? Now we are always interested in comparing those subgroups, like which one should be bigger or which one should be smaller in terms of containment. The operation is containment there. So similar kind of things we have here. So what I want to discuss today is, I want to discuss given a set and topologies on it. How do we compare them? So let me start directly with the definition. So let X be a set and tau1 and tau2 be two topologies on X. Right? Now, number one, if. So how do we compare them? Like subgroups, like vector subspaces, if one is sitting inside other. So if I don't need to write here number one, let me write in one line only. So if tau1 is contained in tau2, we say number one, tau2 is finer or bigger, larger than tau1, and tau1 is coarser, smaller and smaller than tau2. So this is how we compare given two topologies on a set X. So we are often interested in the questions like what would be the largest topology, what would be the smallest topology, these kind of questions. Now, analogous to cyclic subgroups, or algebra generated by a set or a collection, we are interested in the similar kind of things. If you see, cyclic subgroups are nothing but the subgroup generated by a single element. In other words, it's the smallest subgroup containing that element. Algebra, if you don't know about algebra, no issues. If you know, so algebra generated by a set means it is the smallest algebra containing that set. So similar kind of thing we want to develop here. So what we want to do is let X be a set and stylish S, I know this is not stylish, but I only know how to write like this. So stylish S sitting inside X be a subset. Then does there exist smallest topology on X such that S is, or let me write in another fashion. So does there exist smallest topology on X containing script S, So this question and this concept, you see, is actually very useful when we will be discussing, something called subbasis. So what is the answer? As you might have guessed, like groups, subgroups and all. Yes. So let us see why this is true. Let theta, I'm defining a set theta to be tau contained in 2 to the power x such that what I want is tau is a topology containing script S or stylish S. That is what I want to begin with. So this is collection of all topologies which contain script S. Now guys, if this set is empty, then there is no point of this discussion, right? So what's our claim is? Observe that theta is non-empty. Can you guess why? So to think over it for a moment, and then you can stop the video and then you can restart it. So this is non-empty. Why? Because 2 to the power x belongs to theta. Note that 2 to the power x is a topology on X and it contains all subsets of X. So it naturally contains script S. Now this is the, like the biggest, the finest topology which is possible on a set is what? 2 to the power x, because it contains everything, the discrete topology. So it is natural to ask what would be the smallest, right? So that is what we are gonna do. Now, since theta is non-empty, define the notation I want is tau bracket script S, because this topology depends upon script S, to be what? I want smallest, and in which terms? The closest topology. So how we are comparing the two topologies? Using the relation of containment of sets, subset. So what it should be? Like in groups, it should be intersection of all. So intersection of tau belongs to theta tau. So intersection of all topologies which contains S. So clearly, you see, we have proved earlier in some session that intersection of topologies is a topology, right? So by that, tau script S is a topology on what? X. And script S is contained in tau script S, right? This is natural, right? Why? Because every tau or every member of theta contains script S. So it would be an intersection also. Also, by definition, tau is the smallest topology on X containing script S, right? Why? Because it is intersection. So if you still want to argue it, so if T is a topology on X such that T contains script S. So what it means, guys? T belongs to theta. So it means that the intersection of all members of theta is, of course, contain T as a member, right? So this is sitting inside T. So if you want to write it precisely, right? I hope this is clear, and this concept is, trust me, very useful when we will be studying about something called subbases for a topological space. Now, what I want to do next is I want to present examples like how to compare topology, which one would be bigger, which one would be smaller, and like these. So let me begin with that, right? So example 1. There can be many, okay? So I will be discussing a few, and you can try other combinations. So let X is equals to R real line, okay? So it means with the Euclidean topology, the induced by Euclidean metric, and Y to be R COF. You know what is it? Real numbers with cofinite topology. That's what we have, these symbols we have defined last time also. So let us compare these two, okay? Now let U contained in RCOF be open. So what it means, guys? It means R minus U. This is what? Finite. Right? If this is finite, let us assume. Let us give description. Let R minus U to be, say, x1, x2, dot 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 some xm for some m in n, and say x1 is less than x2 is less than dot 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 less than xm. Of course you can assume like that. Why? Because real numbers are ordered, right? You can compare to real numbers. Always you can compare, right? That's not the case with complex, of course. So, now see. This is r minus u. Okay? So, it's just you are removing these are just m points. So this tells me that u is what? U is like this, minus infinity to x1 union x1 to x2 union dot 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 union x m minus 1 to xm union xm to infinity. Now if you see, this is open, right? Where? In R, real line R. This is also. This is these are also open, right? In X, X was a real line. Okay. So what you will get? This implies U is open in R. So you see. So if you assume for a moment, so okay. So if you assume for a moment that the topology on X, this real line, denote topology by tau, just tau, and denote this by tau COF, the usual thing what we have done. So what you have got here, if you take a member in tau cof, it would be in tau, right? So tau cof is contained in tau. So you see what you get here, tau is finer than tau cof. Now guys, tell me, it's possible now that these two topologies are same. So we should always check the other containment also. So let me take a member of tau. Note that open interval 0, 1 belongs to tau, but open interval 0 to 1 does not belong to where? Tau cof, right? Because what is R minus this? It is an infinite set, right? So that's what you see. So what we will get here is, this is strictly coarser than tau. So that is how you compare two topologies. Okay, so what you can do, it would be a very good exercise. So compare, please try comparing tau COC, tau COF, tau, the metric usual one, and tau prime on R, where tau is Usual topology. What I mean by usual, the Euclidean one. I know this E should be capital. I always do this mistake. Euclid was a mathematician. I hope all of you know. He has great contribution to geometry, which we call as Euclidean geometry. And tau prime, R along with tau prime is fourth space. So you know how to define fourth space, right? So take any point of your choice and compare these topologies. Okay. Maybe you can add tau in discrete and discrete. You can compare all of them. Let me discuss one more example. Okay. Now guys, let x is equals to R2 and tau be a topology on x such that every line parallel to y-axis, including y-axis, okay, is an open subset of x along with tau. Basically, every line parallel to y-axis, including y-axis, is a member of tau. It is a subset of x, right? And every line parallel to x-axis, including x-axis, check the spelling of including please here, okay, is also open in x term. Okay, that is what you have given. So I think it is clear. It's a topology where all lines parallel to y-axis, including y-axis, and all line parallels to x-axis, including x-axis, are open sets. Now, compare. What I want to compare is compare this with discrete topology. That is x along with 2 to the power x, where every set is open. That is what the discrete topology is, right? So let us compare it. Now, you can stop the video and try this problem on your own. Now let me begin with the argument. Let a comma b in R2 be arbitrary. Okay? Now, see this diagram. Say your point is here. I mean, it can be in any quadrant, just like as assume it, right? Now, consider this line parallel to y-axis. What should be the equation, guys? X is equals to A. And consider this line which is parallel to x-axis. So what would be the equation of this? Y is equals to B. Right? What is the intersection of these two lines? The point A comma B precisely, right? So now what I want to say is A comma B, singleton A comma B. This is what? Intersection of two sets. What are those sets? X comma Y. In X was our R2. Such that X is equals to A and Y is varying. Intersection X comma Y in capital X, which is our R2, such that Y is equals to B. Right? This is very clear. This intersection is very clear. I think no justification, more justification is needed. Now guys, this is open, right? In tau. Remember what tau was? Every line parallel to x-axis and y-axis, including the axis, both axes, are open sets in tau. That's the only information we know about tau. This is also open in tau, right? Tau is a topology. Finite intersection of open set is open. So what this implies? This singleton A comma B is open in X along with tau for every A comma B in X. X was our R2. So what you get, I think this argument I have already told you in one session. I have hinted you. So what you will get here is, this implies every subset of X is open with respect to tau. So what it means, guys, tau is equal to 2 to the power x, which was your discrete topology, right? Tau is equal to 2 to the power x. So you see, this is a nice example, right? Let me have a remark. This is a very important remark. Above exercise tells us that sometimes few members of a topology can describe whole topology, right? Right? So only a few members, right? We have just mentioned few subsets which are open in above example, and what we get all open subsets, right? So this motivates us to discuss something called bases and subbases for a topology. So remember this motivation when we would be starting with bases and subbases after some time, not now. I mean, we have a few things to discuss before coming to this topic, bases and subbases, but this is the prime motivation for that. Why? Because it is analogous to your vector spaces, right? In vector space also you have a basis, right? So what that basis do? That is only some elements, that basis contains some elements which describes the whole vector space, right? Every element of that vector space you can write in combination, linear combination of the basis element. What kind of basis I am talking about? Hamel basis, right? You might have studied two kinds of bases, Hamel and Schroeder basis. So the basis of vector space I was talking about is Hamel basis. So similarly, we have similar kind of things happening here, right, in above example. So we would be discussing these two concepts, but after some time, not in the coming session, because we need to do a few more things which are important to discuss in the beginning. So let me end here. Thank you very much, guys. See you next time.